Isolation transformers are essential for electrical safety and equipment protection. When seeking more efficient designs, several options surpass traditional toroidal transformers. Firstly, amorphous core transformers utilize a non-crystalline metal alloy core, significantly reducing core losses and increasing efficiency. Secondly, nanocrystalline core transformers, similar to amorphous core types, employ a nanocrystalline metal alloy core for even lower core losses, pushing efficiency even further. Thirdly, autotransformers present another alternative. Unlike isolation transformers with separate primary and secondary windings, autotransformers have only one winding with a tapping point to provide voltage transformation. This design is generally smaller and lighter than conventional isolation transformers. To create a lighter isolation transformer, several strategies can be employed. 1. Using lightweight materials is crucial. Substituting steel enclosures with aluminum can significantly reduce weight. 2. Optimizing the winding design can minimize the amount of copper and insulation needed, resulting in a lighter transformer. 3. Reducing the core size. By selecting an appropriate core size for the required power level, the overall weight can be reduced. Power density, measured in kilovolt amperes per unit weight, is a key factor. Toroidal designs typically offer a high power density in conventional transformer designs. Cooling requirements also play a vital role. Higher efficiency transformers generate less heat, which can reduce cooling needs and allow for a lighter design. A custom design can also optimize size, weight, and efficiency for specific requirements. Working with a reputable transformer manufacturer to create a custom transformer ensures tailored performance. Here are some manufacturers that specialize in lightweight and efficient isolation transformers. Elgert Toroid Corporation, Sumitomo Electric, and Solar HD. These companies offer a range of transformers designed for optimal performance and weight reduction. When evaluating isolation transformers, consider the total cost of ownership. While more efficient designs may have a higher initial cost, the long-term savings from reduced energy consumption and potentially lower cooling requirements can outweigh the initial investment. The choice between different transformer designs depends on specific application requirements, budget constraints, and desired performance characteristics. Carefully consider all factors to select the most suitable isolation transformer for the job. When selecting an isolation transformer, it is important to consider several factors to ensure it meets the specific requirements of the application. Firstly, voltage and current ratings are critical. The transformer must be able to handle the input and output voltage and current levels without overheating or experiencing premature failure. Secondly, the isolation voltage rating must be sufficient to protect personnel and equipment from electrical shock. This rating specifies the maximum voltage that the transformer can withstand between its primary and secondary windings. Thirdly, frequency response should match the application. The transformer's frequency response should be adequate for the intended application. Some transformers are designed for use with specific frequencies, such as 50 Hz or 60 Hz, while others can operate over a wider range of frequencies. Fourthly, consider the power rating, which must be adequate for the load. The transformer's power rating, measured in kilovolt amperes, must be sufficient to handle the load requirements. Overloading a transformer can cause it to overheat and fail. Fifthly, efficiency is key. Higher efficiency transformers consume less energy and generate less heat, which can reduce operating costs and improve overall system performance. Sixthly, consider the impedance. The transformer's impedance affects the voltage regulation and short-circuit current levels. It should be selected to match the requirements of the application. Seventhly, the size and weight must meet any limitations. The transformer's size and weight can be important considerations, especially in space-constrained applications. Eighthly, regulatory compliance is necessary. Ensure that the transformer meets all applicable safety and regulatory standards, such as those set by Underwriters Laboratories, Canadian Standards Association, and the International Electrotechnical Commission. Finally, environmental conditions must be suitable. The transformer's operating environment, including temperature, humidity, and altitude, should be considered. Some transformers are designed for use in harsh environments, while others are better suited for indoor applications. In addition to these factors, it is also important to consider the transformer's construction and materials. High-quality materials and construction techniques can improve the transformer's reliability and longevity. For example, transformers with copper windings and high-grade insulation tend to be more durable than those with aluminum windings and low-grade insulation. The core material is another important consideration. Amorphous and nanocrystalline cores offer lower losses and higher efficiency than traditional silicon steel cores. The type of enclosure used to protect the transformer can also affect its performance. Enclosures should be selected to provide adequate protection from environmental factors such as moisture, dust, and corrosion. Cooling methods also play a significant role in transformer performance. Transformers can be cooled by natural convection, forced air, or liquid cooling. The appropriate cooling method depends on the transformer size, power rating, and operating environment. Natural convection is typically sufficient for smaller transformers, while forced air or liquid cooling may be required for larger transformers or those operating in high-temperature environments. When selecting an isolation transformer, it is important to consult with a qualified electrical engineer or transformer manufacturer to ensure that the transformer meets all of the application's requirements. They can help you evaluate the various options and select the best transformer for your needs. Regular maintenance is essential to ensure the continued performance and reliability of an isolation transformer. Maintenance tasks may include inspecting the transformer for damage, cleaning the transformer, tightening connections, and testing the insulation resistance. The frequency of maintenance depends on the transformer's operating environment and application. Transformers operating in harsh environments or critical applications may require more frequent maintenance. Safety precautions should always be followed when working with isolation transformers. Transformers can operate at high voltages and currents, which can pose a serious electrical shock hazard. Only qualified personnel should perform maintenance or repairs on isolation transformers. Always de-energize the transformer before performing any work and use appropriate safety equipment, such as insulated gloves and tools. Grounding is also essential for safety. The transformer's enclosure should be properly grounded to prevent electrical shock. The grounding conductor should be sized according to applicable electrical codes. In addition to safety, proper installation is also important for transformer performance. The transformer should be installed in a location that provides adequate ventilation and protection from environmental factors. The transformer should be mounted securely to prevent vibration and damage. Wiring connections should be made according to the manufacturer's instructions and applicable electrical codes. Surge protection is another important consideration. Isolation transformers can be vulnerable to voltage surges caused by lightning strikes or other events. Surge protection devices can be installed to protect the transformer from damage. These devices should be selected to match the transformer's voltage and current ratings. Harmonic distortion can also affect transformer performance. Harmonics are unwanted frequencies that can cause transformers to overheat and fail. Harmonic filters can be installed to reduce harmonic distortion and improve transformer performance. Monitoring the transformer's operating parameters can help identify potential problems before they become serious. Key parameters to monitor include voltage, current, temperature, and insulation resistance. Monitoring can be performed manually or automatically using sensors and data logging equipment. When selecting an isolation transformer, it is also important to consider the transformer's life expectancy. The life expectancy of a transformer depends on several factors, including its design, materials, operating environment, and maintenance practices. Well-designed and maintained transformers can last for many years. When a transformer reaches the end of its life, it should be disposed of properly. Transformers contain materials that can be harmful to the environment, such as oil and heavy metals. These materials should be recycled or disposed of according to applicable regulations. In addition to the technical aspects of isolation transformers, It is also important to consider the economic aspects. The cost of an isolation transformer can vary depending on its size, features, and manufacturer. The total cost of ownership should be considered, including the initial cost, operating costs, and maintenance costs. Energy-efficient transformers can help reduce operating costs and improve overall system efficiency. Retrofitting existing transformers with energy-efficient models can also be a cost-effective way to improve energy efficiency. Transformer manufacturers can provide information on the energy efficiency of their products and help you select the best transformer for your needs. In summary, selecting and maintaining an isolation transformer requires careful consideration of several factors, including voltage and current ratings, isolation voltage rating, frequency response, power rating, efficiency, impedance, size and weight, regulatory compliance, environmental conditions, construction and materials, cooling methods, safety precautions, installation practices, surge protection, harmonic distortion, monitoring parameters, life expectancy, and economic aspects. By considering these factors, you can ensure that the isolation transformer meets the specific requirements of the application and provides reliable and safe operation. Working with qualified electrical engineers and transformer manufacturers can help you make informed decisions and select the best isolation transformer for your needs. Continuous learning and staying up to date with the latest technologies and best practices are also essential for ensuring the continued performance and reliability of isolation transformers. This includes attending industry conferences, reading technical publications, and participating in training programs. By staying informed and engaged, you can contribute to the advancement of isolation transformer technology and improve the safety and efficiency of electrical systems. In addition to the points already discussed, it's worth noting the advancements in smart transformer technology. Smart transformers incorporate sensors, communication interfaces, and advanced control algorithms to provide real-time monitoring and control of transformer performance. These features can help improve efficiency, reliability, and safety. For example, smart transformers can automatically adjust their voltage and current levels to optimize performance and reduce energy consumption. They can also detect and diagnose potential problems before they lead to failures. The use of smart transformers is becoming increasingly common in modern electrical grids and industrial facilities. Another area of development in isolation transformer technology is the use of solid-state transformers. Solid-state transformers use semiconductor devices to perform voltage transformation, rather than traditional magnetic cores and windings. Solid-state transformers offer several advantages over traditional transformers, including smaller size, lighter weight, higher efficiency, and improved controllability. However, they also have some disadvantages, such as higher cost and lower power handling capability. Solid-state transformers are currently being used in niche applications, but they are expected to become more widespread in the future as their cost decreases and their performance improves. Furthermore, the choice of insulation material is critical for transformer longevity and safety. Traditional insulation materials like mineral oil are being replaced or augmented with newer, more environmentally friendly options like ester fluids. These fluids offer improved fire resistance, biodegradability, and electrical performance. When selecting a transformer, carefully consider the insulation material and its properties. Consider also the specific testing and certification requirements for your application. Standards organizations like the Institute of Electrical and Electronics Engineers and the International Electrotechnical Commission provide detailed testing procedures and certification programs to ensure transformer safety and performance. Compliance with these standards is essential for ensuring that the transformer meets industry best practices. Finally, remember to document all transformer-related activities, including installation, maintenance, testing, and repairs. Maintaining accurate records can help you track transformer performance, identify potential problems, and plan for future replacement. Proper documentation is also essential for compliance with regulatory requirements.